Earlier, I promised you a couple of other more formal techniques for integrating that give you sort of a more step-by-step approach than the guess and check method that we've talked about earlier. And this is the first of these. We'll call it method 2 and refer to it as substitution by matching just for convenience. The trick here, when you're using method 2, the substitution by matching, is to fit a given integral into the general power rule for integration formula by matching the differentials. And it's probably easiest just to do it through an example to show you how it will all work. Always keep in mind that you cannot force the integral to fit into the general power rule formula unless it actually does fit. Just keep that in the back of your mind. I promised you to show you how to do it through an example. So suppose we're trying to integrate this integral whose integrand is 4x times the quantity x squared plus 1 cubed. Here's what you do. You set u equal to the expression raised to the power. Here that would be the x squared plus 1. So you set u equal to x squared plus 1. Step 2, compute du dx, the derivative of u with respect to x. So that would be 2x. Step 3, solve for du. So I'll multiply both sides by dx. Notice that the dx is on the left, divide out. And that gives you du, which in this case is 2x dx. Step 4 says if the integrand has a numeric factor, move it outside the integral. Here there's a factor of 4 being multiplied inside the integrand, so I'm going to move it outside the integral. Step 5 says to reconstruct the integrand so that the u part is followed by the du part. This is beginning to get to the heart of the process. The u part is the part that involves the thing we call u. But when I say u part, I'm including the exponent as well. So I'm calling here the u part the x squared plus 1 raised to the third power. Everything else in the integrand is the du part. So the dx is part of the du part, but that x on the far left is also a part of the du part. In other words, everything that's not part of the u part is by default part of the du part. But the step says that the u part should be followed by the du part, not that it sits in the middle of the du part. So what we're going to want to do is rearrange the terms. So instead of having the x sit on the far left, we move it over to the right so that it sits just to the left of the dx. Now step 5, having said reconstruct the integrand so that the u part is followed by the du part, is satisfied, is followed by the du part, whereas before the u part was sitting right in the middle of the du part. So there's step 5. Remember though that we can always compensate by a constant factor if we need to. Now what do I mean by that? We're trying to match the differentials. That's the reason this is called substitution by matching. And if I look back up where I calculated du needs to be 2x dx. But if you look back down at the integrand, the way I've done it, there is no 2. But step 5 says we can compensate by a constant factor if needed. 2 is a constant, just a number. So I'm allowed to put that 2 in there. But if I do, I have to compensate by multiplying by the reciprocal on the outside. So if I multiply by 2 on the inside, I have to multiply by 1/2 on the outside. Then we want to substitute the u's and the du's into the integral and get rid of the x's and dx's entirely. So when you finish the substitution part, there will no longer be any x's or dx's. And you can see how this works. Also, I would say that if it helps you to actually label them, you can do that. The x squared plus 1 is what we're going to call u, and the 2x dx is what we're going to call du. So when you actually do the substitution, the x's and everything with an x or a dx in it pops out. Notice also I went ahead and simplified the 1/2 times 4. The 1/2 times 4 is 2. Then you've got the integral. The thing raised to the third power becomes u, and everything after the u is du. That's the reason that step 5 says to have the du part following the u part so that it works out just this way. Now, once you get it to this point, you can see the end, I think. You're now going to use the power rule for integration. Keep copying that 2 down. The 2 is multiplied by the integral. You're not doing anything with it right now, but you do have to keep copying it down. If you forget it, you're going to be off by a factor of 2 in the end. But now we're concentrating on the integral of u to the third. Well, the general power rule for integration says that you're going to increase the power by 1. Well, there's a 3 in the integrand, so when it comes out and you've integrated, it's going to be u to the fourth. But not only that, it's multiplied by 1 over that new power. 1 over something is the reciprocal of it, so if the new power is 4, you have to multiply by 1/4. And as always, you add a plus c. Now you've done all the integration. 2 times a fourth is just 1/2. But the original problem had no u's in it. So the very last step is to substitute the x values back in for your final answer. Well, we know from the upper right of that gray box that u is equal to x squared plus 1. Once we've done the integration, we put the x squared plus 1 back in place of u, and we get 1/2 times the quantity x squared plus 1 raised to the 4th power plus c. And as always, if you're ever in doubt that that's correct, you can go back and check that by taking the derivative of the answer and make sure you get what you have in the original integrand. I won't do that here, but anytime you feel like you aren't sure, you can always check it. This is the step-by-step 1, 2, 3, 4, 5, 6, 7, 8. You've got it. Practice makes perfect on these things. I'll also say that if you go back, we worked this exact same problem by the guess and check method. If you go back and look at that problem when we worked it back then, you'll notice, and I've circled both of them, those 2 answers are the same. You don't have to do this one by substitution by matching. You can go back and do it by guess and check. Or you can forget guess and check and do it by substitution by matching. So as you go through these problems, what you need to be thinking about is, what method do I understand the best? Which makes the most sense to me? And then you practice doing it that way. So this is a great example of how to carry out a substitution by matching. And it's the first method that's a little more formal than what we were doing with guess and check. What I want to do next is give you 6 examples, and each one of them models a step-by-step solution technique using substitution by matching. What I'd like for you to do is look at each problem, pause everything, try to solve it yourself, and then make your way through the step-by-step solution. And if you got it right, just seeing someone else do it step by step should build your confidence. And if you got stuck at some point, you can see where you went wrong as you go through these step-by-step solutions. And there are 6 of them. It gives you lots of opportunities to practice and to get some step-by-step help if you get stuck. But what I don't want you to do is just sit there and watch, and not pick up anything to write with. I would love for you to take this seriously enough that you would write each problem down, try to solve it, and then watch the solution step by step and compare it to what you were doing. The only way you learn math is by doing math. So take this seriously. Mastery takes lots of practice. Unfortunately, there's no shortcut. Suppose we wanted to evaluate this integral, and suppose I want to evaluate it using what I call substitution by matching. These are the steps, and although it might look daunting on first glance, as you practice more and more, you'll get into the flow of it and see that it's really not bad at all. Before we begin this solution, let's go ahead and recopy down the original problem. Step 1 says that we need to set u equal to the expression that's raised to the power. That would be the x minus 6. So we let u be x minus 6. Step 2 says to calculate du dx, which that would be the derivative of x minus 6 is just 1. As you can see from step 3, we want to solve for du. That was our ultimate goal anyway. So what we want to do is multiply both sides by dx, and that will let us solve for du. We find out that du is 1 dx, or just dx. Now step 4 says if the integrand has a numeric constant factor, move it outside the integral. Well, there is no numeric factor inside the integral. The numeric factor, if there were one, would be something inside the integral that's just a number, like 5 times that, or 7/2 times that. There is not one here. So there is nothing to worry about with step 4. Step 5 says to reconstruct the integrand so that the u part is followed by the du part, remembering that we can compensate by a constant factor if needed. Now that's a lot of words, but all it's asking us to do is to look at what I'll call the u part. That's the x minus 6. The u part would be all of that. And the du part is the part that's associated with dx, and in this case du and dx are equal to each other. So we want to make sure that the u part comes first and is followed by the du part. So if this is the u part here and this is the du part, then in fact 5 is already satisfied. The du part is at the end, and that's what we're trying to do. We're trying to get the entire du part at the end. Step 6 says to substitute. You plug the u value in and the du value in. And what you have to remember is that this substitution is based on what you let u be equal to. We let u be equal to x minus 6, so this x minus 6 becomes u. So in substituting it in, the integral becomes not x minus 6 to the 3/2 power, but u to the 3/2 power. And the du and the dx are equal to each other, so if I substitute out dx, I plug in du instead. Now this is a perfectly simple one because we don't even have to make an adjustment. That's an exact substitution. You have to get rid of all your x's and replace them with u's. So in the original problem, you've got all x's and dx's. In the properly substituted integral, you only have u's and du's, and that's what happened here. Now once we get to that point, you can see where we're going. That brings up the general power rule for integration. The general power rule for integration tells us exactly how to integrate u to a power. You add 1 to the power, and then on the outside, you multiply by the reciprocal of that power. So whatever the power is, you multiply by 1 over that power. So in our case, when we integrate, we add 1 to 3/2. I hope you don't really have to spend much time thinking about this, but if you add 1 to 3/2, remembering that 1 is 2/2, you end up with a power of 5/2. So when you integrate, you're going to get a power of u to the 5/2. Now, out front, you have 1 over that power. Well, the power is 5/2, so you have 1 over 5/2. Now I could write it as 1 over 5/2 and then simplify it, but 1 over a fraction is just the reciprocal of the fraction, so it's easier just to go ahead and invert it before you even write it down. So this 1 over 5/2 becomes 2/5 because 1 over a fraction is just the reciprocal of the fraction. And of course, for all our indefinite integrals, you have a constant of integration plus c to take care of the case that there was a number added to the end of that, because when you go back and take the derivative of a number, it becomes 0, and so you can't tell if there was in fact a number added. So by doing the substitution by matching, we were able to evaluate the integral, but remember the original problem did not have a u in it. So when you're done, you've got to substitute the x values back in. So now you've got to go back and say, well, u is really x minus 6, so I end up with 2/5 times x minus 6 quantity to the 5/2 power plus c. And there you go. integration using substitution by matching. I do want to say two things about this problem. If you go back and look, you can find a problem that's identical to this one that was solved by what I called method 1, which is guess and check. And if you're curious, you can go back and look at that problem and notice that you get the same result either way. So, if you want to use guess and check, that's fine. If you want to use substitution by matching, that's okay too. The second thing I want to say about it, and you'll see this if you look around a little bit when we're doing the same problem using method 3. This problem is so simple that method 2 and method 3 are identical to each other. That's not always the case. Otherwise, why would you call one method 2 and one method 3? But in this particular case, and what happens is du and dx are the same thing. Whenever that happens, method 2 and method 3 collapse into each other, and they give you the same exact steps. When all is said and done, the integral of the quantity x minus 6 to the 3/2 power is 2/5 times the quantity x minus 6 raised to the 5/2 plus the constant of integration c. Suppose we wanted to evaluate this integral, and suppose I want to evaluate it using what I call substitution by matching. These are the steps, and although it might look daunting on first glance, as you practice more and more, you'll get into the flow of it and see that it's really not bad at all. Before we get started, I want to go ahead and copy the problem back down again. Now, looking up at our steps, step 1 says that we need to let u be equal to the expression raised to the power. That, in this case, would be x minus 6. Step 2 says to compute du over dx. Du over dx would be 1. Step 3 says to solve for du. So I just multiply both sides by dx, and I find that du is equal to 1 dx, or just dx. Step 4 says if the integrand has a numeric, which means a constant factor, move it outside the integral sign. Now there is a 2 here, which is a numeric factor. So I'm going to move it outside of the integral sign. Step 5 says the integrand must be reconstructed so that the u part is followed by the du part. And remember, you can always compensate by a constant factor if you need it. You can put the constant factor inside the integrand and compensate by multiplying by its reciprocal on the outside. You're always allowed to do that. Here, we're also concentrating just on the integral part. The 2 just sits there. The 2 doesn't go away. It's going to be 2 times something. But we don't worry about the 2. We just carry it along for now. We're interested in the integral itself. So the u part is the part that's raised to the power. And when I say u part, I'm also including the exponent as well. So the u part is x minus 6 quantity raised to the 3/2 power. The du part is the rest of the integral. In other words, everything else to the right of the integral sign. And the only thing left inside the integral to the right of the integral sign is the dx. So that is the du part. It's everything else. Now keep in mind that 2 doesn't vanish. We don't do anything with it right now, but it just carries along. Step 6 tells us substitute for the u and the du. Now remember, the u part is the part associated with the x minus 6. So if we're actually going to do the substitution in the integral, the x minus 6 becomes the u to the 3/2 power. The u part followed by the du part, which we said was dx. The dx is du. And that's our substitution. Be careful to see what's happened. This is the u part. That corresponds to the u part in the original with x's in it. And this is the du part, which corresponds to the du part up here. So we've completely eliminated all the x's and dx's and replaced them with u's and du's, which is the goal. I'm going to rewrite that integral without all the clutter. I'm not changing anything, I'm just getting rid of some of the clutter. So I get the integral of u to the 3/2 du. And of course it's still multiplied by 2. Keep in mind that I'm doing this substitution so that I can fit the integral into the general power rule for integration, which tells me if I have an integral of the form u to the n, I can evaluate it by raising the power of n by 1 and compensating by multiplying by its reciprocal 1 over n plus 1. So, go up by 1, 3/2 plus 1. I hope I don't need to go through this, but I will. 1 is 2/2, so 3/2 plus 1 is 3/2 plus 2/2, which is 5/2. So by the general power rule for integration, the integral of u to the 3/2 is going to have a power of 5/2, but it's going to be multiplied out front by its reciprocal, 1 over 5/2. Now, I could write 1 over 5/2, but the reciprocal of a fraction is just the fraction turned upside down, so that would be 2/5. And don't ever forget the plus c, because we're doing an indefinite integral, and you always have to say plus c to allow for the possibility that there was a constant added in there or subtracted whose derivative is 0. There's no way to know, so you put the plus c. And of course, 2 times 2/5 is 4/5, so we end up with 4/5 u to the 5/2 plus c. We're done with the integration, but remember the problem didn't start out with u's in it, so we have to get rid of the u's by going back and remembering what u is. U is x minus 6, so we go back in and we write 4/5 times the quantity x minus 6 to the 5/2 power plus c. And there's your solution. Suppose we wanted to evaluate this integral. And suppose we wanted to do it by our method of substitution by matching. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. And then start at step 1. Step 1 says to set u equal to the expression raised to the power. Well, u is x squared plus 3 then, because x squared plus 3, that quantity is raised to the 3rd power. Step 2 says to compute du dx, that's the derivative of u with respect to x. That's easy enough. The derivative of x squared is 2x and the derivative of 3 is 0. So du dx is simply 2x. Step 3 says to solve for du. Again, easy enough. Just multiply both sides by the quantity dx. The dx is on the left, divide out, and you find that du is 2x dx. That takes us through the first 3 steps. They flow together nicely. Step 4 says if the integrand has a numeric, that means just a constant, just a number. If it has a constant factor, move it outside of the integral. Well, here the 8 is definitely a constant factor inside the integral, so we'll move it outside. We can always take a constant factor outside of the integral sign. First 4 steps, very straightforward. They sort of flow into each other. Step 5, read it closely, take it step by step. Step 5, first of all, says to reconstruct the integrand so that the u part is followed by the du part. And then remembering that we can compensate by a constant factor if needed. In other words, we can insert a number as a factor inside the integral as long as we compensate by multiplying by its reciprocal on the outside. If we need to do that, we can. But let's go back to the first part, which says to put the u part part first, followed by the du part. Well, that should be easy enough because we're looking at that integral. The 8 is just sitting there. It's still going to be part of the answer, but we're not focused on it right now other than to keep copying it down. We're focused on the integral itself. And step 5 says to put the u part first. Well, remember, looking back over at the setup when we found out what u was in the beginning, u is equal to the x squared plus 3, so the u part is not only the base, the thing that we call u, but it's also inclusive of the exponent. So the u part is u to the third. It's the expression raised to the third power, not just the thing we call u. Once you get used to that, it's easy enough to remember. So we want to put, according to step 5, the u part first. What about the du part? Well, the du part is always going to have the dx and whatever else is in the integrand that didn't get absorbed into the u part. And that would include not only the dx, but also the x. So looking back at the integrand, both the x and the dx are part of the du part because they're not part of the u part. The du part is everything that didn't go into the u part. Now step 5 says to put the u part first. So if you want to remember that as you're going along, you're going to put the u part first, and everything that's not in the u part is going to go to the right of the u part and is going to get absorbed into the du part as well. But the 8 just follows along for the ride. So just keep writing the 8 down, focusing back on the integral. I'm going to do exactly what step 5 says. It says to put the u part first. Well, the u part was the x squared plus 3 to the third. That's the u part. It needs to go right after the integral sign. Everything else is going to go next. So that x that used to sit just to the right of the integral sign, because it's going to be part of the du part, gets moved over next to the dx. So far, so good. We've done what step 5 says down to the part where it says remembering. So let's read that part. Remembering that we can compensate by a constant factor if needed. Well, is it needed? And the way you tell is by looking back at your du. And if you look back down here at the du, you will notice that there's a 2 sitting there. But there's no 2 sitting up in front of the x dx in the du part in the integral. That's what you need to know. Because the 2 down here, where the du is determined, is not present in the integral itself, that means that we have to indeed compensate by a constant factor, that factor being the 2 that's missing. There's no 2 in that integral, but we need a 2. But we can do that. All we have to do is go to the du part, put in a 2. Now it's there. That's okay as long as you multiply by the reciprocal on the outside of the integral sign. So far, so good. We can do our little arithmetic along the way as we go, so you might as well go ahead and say that 8 times a half is 4. And now we can focus on the integral again. And the integral itself can be substituted because now we've just gotten to step 6, which says to substitute the u and the du. Notice that the x squared plus 3 is what we called u. So that's where the substitution comes in. We actually call it u. But what about the rest of the integral? The rest of the integral has this 2x dx. That's the du part. What about that? Well, that's what we call du. If you look over here, that's the du. So it's just a direct substitution. The x squared plus 3 turns into u. The 2x dx turns into du. And of course, that 8 times 1/2 makes 4. We're down through step 6 now. But don't ever forget that we're still focusing on the integral itself. That numeric factor, whatever it happens to be, in this case a 4, just sits there. It will eventually get multiplied through, but right now it just sits. We're interested in that integral here. And as a matter of fact, in order to finish this off, we probably want to get rid of some of that clutter. So let's take some of that clutter away. After you copy the 4 back down, the integral itself should remind you of the general power rule for integration, which says that we can evaluate the integral of u to a power, and we do that by increasing the power by 1 and multiplying by the reciprocal, or 1 over the power on the outside. We've been doing that for a while, so that should be fairly straightforward. So if we want to integrate u to the third using the general power rule for integration, the new power will be 1 higher, which makes 4, but we have to multiply by 1/4 on the outside. But please don't forget that this 4 is still sitting there. So that 4 does not go away. And in fact, it will multiply by the 1/4 to give us 1 eventually. The other thing you don't want to forget is that this is an indefinite integral. You have to put plus c. That allows for the possibility, if you're thinking backwards, of this integral being an antiderivative. If you went back and took the derivative of the antiderivative, if there were just a number added, its derivative would be 0. So there's no way to tell if there was a number or not. So you put a plus c to allow for that possibility. And now the hard part's over. 4 times 1/4 is just 1, so you get 1 u to the 4th plus c, or just u to the 4th plus c. We've done the calculus now, but keep in mind there was no u in the original problem. We introduced the u. So the last step is to take the u back out. U was equal to x squared plus 3, so it becomes quantity x squared plus 3 to the 4th power plus the constant of integration c. And that's the answer. Remember, you can turn right around and take the derivative of your answer and prove to yourself that you really do get what's between the integral sign and the dx for its derivative, and that can assure you, if you're a little bit hesitant whether you did it correctly or not, that can assure you that you in fact did get it right, or conversely, if you did make a mistake, it'll show up when you take the derivative of the answer and see that it really is not equal to the integrand. Either way, taking the derivative of your answer and checking it against what you started with is not a bad strategy. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of substitution by matching. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Now we can just begin going through the steps one at a time. The more you practice this, the more it will all flow nicely. The first step is to set u equal to the expression raised to the power. In this particular case, that might be slightly confusing since there's more than one thing, obviously, raised to power. You've got 3x to the 4th. In the numerator, you've got the expression x to the 5th plus 1, all raised to the 3rd, in the denominator. Whenever there's a choice that you have to make and you're not quite sure, I think this tip will probably help you. As you get further along, I think you'll see that it becomes a more natural problem. But in the beginning, you need something to sort of guide you. And I would give you this tip. If you're ever in doubt about what to choose u on the source of problems we're dealing with now, you probably should choose u to be the expression with the highest power. So in the numerator, you've got a 3x to the 4th, but in the denominator, you've got that x to the 5th plus 1. That's a higher power. That's probably going to be a good guide for you whenever you're thinking there might be more than one choice. So that's what I'm going to do. I'm going to let u be the expression x to the 5th plus 1. Step 2 says to compute du dx. That's just the derivative of u with respect to x. The derivative of x to the 5th plus 1 is 5x to the 4th. And then if we want to solve for du, which is step 3, we simply multiply both sides by dx. The dx is on the left, divide out, and you'll see that du is equal to 5x to the 4th dx. So we've done steps 1, 2, and 3. Step 4 says if the integrand has a numeric which is just a constant or just a number factor. Factor is a number that's multiplied by something else. Move it to the outside of the integral. And you notice there's a 3 there. Let's move it to the outside of the integral. That leaves us with just an x to the 4th in the numerator. Now this 3 out front is just going along for the ride. What we're actually going to be working with is this integral. Granted, that 3 will multiply our final result, but what we're interested in, other than carrying that 3 along with us, is that integral. Now looking at that integral, we've identified that u is x to the 5th plus 1, and that the u part, what we're calling the u part, includes the power as well. So the u part is the quantity x to the 5th plus 1 all cubed. And everything else is going to be part of the, what I call the du part. Now remember, we're just carrying the 3 along for the ride, but don't forget to keep doing that. So we'll write the 3 down, but we're looking at that integral, and step 5 tells us that we need to get the du part after the u part. So I know that x to the 4th is part of the du part, so I'm physically going to put that x to the 4th with the dx, because I know that they belong together. X to the 4th dx, x to the 4th dx. Now, once I grab that x to the 4th from the numerator and there's nothing else up there, that's not going to do. I've got to do something, and what I do is put a 1 there, because if I put that x to the 4th back to where it was, 1 times x to the 4th is still x to the 4th, and I haven't changed anything. So if I pull the entire numerator off, I have to put a 1 there. So look at what we've got. We've got the u part right after the integral sign, and the rest of it is the du part. Now going back to number 5, it says to do just what we did, but then it ends by saying that if we need to compensate by a constant factor, we can. So we have to answer that question, do we need to do that? And you answer that by looking back down at the differential du in the lower left, and you'll see that yes, there's a 5 there that doesn't appear back in the integral. There's just an x to the 4th dx, but we need a 5 x to the 4th dx. So as a matter of fact, we do have to compensate by putting a 5 as a factor in the du part. So I will put that 5 there. I can do that as long as I compensate by putting a 1/5 on the outside. Look very carefully at that, because if you're confused about how that worked, then anything you do from here on will be a waste of your time, because you're not following along at this point. So pause if you have to. Make sure you understand how we got there. And by the way, before we go any further, we might as well take care of the arithmetic here out front of the integral sign and multiply 3 times 1/5. Of course, that's just 3/5. Now you can see that we're ready to go to step 6, which is to actually do the substitution. Take the x's and dx's out and replace them with u's and du's. So what is u? U is x to the 5th plus 1. So out goes x to the 5th plus 1, and it's replaced by u. Okay, what about the rest of it? Well, the 5x to the 4th dx, what I call the du part, is in fact equal to du if you look down the bottom left. So all of that can come out, and we just call it du. So the 1 over something to the 3rd becomes 1 over u to the 3rd, and everything else, as you can easily see, is equal to du. So my substitution now is complete. No longer have any x's and dx's, I only have u's and du's. That's the goal of this whole substitution by matching, is to make things so that you can, in one fell swoop, get rid of all your x's and dx's and replace them with u's and du's. It's quite a trick. Now what? Well, remember, we're eventually going to use the general power rule for integration, but that applies to u to a power. This is 1 over u to a power. So what happens here? Remember, we're talking about the u to the third as being the u part and the du being the du part. We substituted out of there, but that still does not fit the formula that we want to use. We want to integrate that integral right there, but the formula we have starts us off with an u raised to the n power, not a 1 over u raised to the n power. Turns out that's simple to solve because 1 over u to a power is just u to the negative of that power. So writing the 3/5 down again, I know that 1 over u to the third is just u to the negative 3. Just basic algebra. So now the integral looks like something that I can deal with. So again, I'm just carrying that 3/5 along. Please don't forget to carry that 3/5 along. Your constant factors always get carried along. I'm going to now take the integral that matches the general power rule for integration formula, and I'm going to apply the general power rule for integration. It says when you've got u to a power, you can take the integral by adding 1 to the exponent as long as out front you multiply by 1 over that exponent. Now be careful with negative exponents. If I add 1 to minus 3 plus 1 is minus 2. So be very careful with that. So it becomes u to the minus 2, and then according to the general power rule, we want to multiply by 1 over that power. So if minus 2 is the power, we've got to multiply out front by 1 over minus 2. Keeping in mind that that 3/5 is still sitting there. Also remember that, as always, with indefinite integrals, you have to add a plus c. We're close now. Let's do the arithmetic out front. Multiplying a positive fraction times a negative fraction is going to give me a negative fraction. And when you multiply fractions, you do top times top, bottom times bottom. So you get negative 3/10. And you still have the u to the minus 2, and you still have the plus c. We've done the calculus. We're basically done. But we're the ones that put the u in the problem. There was no u in the original problem, so we have to get rid of the u as the last step. Now I've run out of room down here, so let's just take that and put it up at the top and keep going from there. So as I was saying, I want to get rid of the u and put the x's back in. But that's easy enough because I know that u is equal to x to the 5th plus 1, so I just got to go back and put that in there. Take that x to the 5th plus 1, plug it in place of u, and you have your answer. Also remember that if you're at all unsure that you did it correctly, all you have to do is take the derivative of your answer and see if it comes out to be the integrand that you started with. So if you take the derivative of your answer and it comes out to be the integrand that I've circled there, then you can be very confident that you have the right answer. Practice is the key. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of substitution by matching. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Now, because the general power rule for integration, which we'll be using eventually, doesn't deal with radicals, the very first thing I want to do here is change that square root to a 1/2 power, because that's what the general power rule for integration works with. It works with powers. So I'll rewrite that using a 1/2 power instead of a square root. Now let's start using the steps. The first step says to set u equal to the expression raised to the power. Now I'll say this, if you have any doubt about what you should choose for u, here's a little tip. For what we're doing now, and as you get used to this process, this tip will usually get you where you need to be. And that tip is, if you're in doubt, choose u to be the expression with the highest power. So if you look in this integral, there's an x minus 3, that's x to the first power. But down in the denominator, you've got an x squared minus 6x plus 1. That's a higher power. So my tip would say, choose that to be u. So I'll do that. Let u equal x squared minus 6x plus 1. Step 2 is to compute du dx. That's the derivative of u. That would be 2x minus 6. And our ultimate goal, which is what step 3 is to solve for du. So I'll multiply both sides by dx. The dx is on the left, divide out. And I end up with du equal to the quantity 2x minus 6 multiplied by dx. Now, another little tip, if you like, whenever you see a differential that has a common factor that can be factored out, most of the time you're going to want that factored out. So I'm going to take the common factor of 2 and factor it out of that and go ahead and write du as 2 times the quantity x minus 3 times dx. And you can probably see now why that was a good idea, because if you look back into the numerator of the integral, you'll see that x minus 3. And you can see the wisdom of factoring that 2 out here. In any case, step 4 now says if the integrand has a numeric constant factor, you can move it outside the integral. There is no numeric constant here, so we don't have to worry about it step 4 this time. So we can move right along to step 5. Step 5 says to reconstruct the integrand so that the u part is followed by the du part, remembering that we can compensate by a constant factor if needed. So the u part is the part associated with what I called u, including the exponent. So u is the quantity x squared minus 6x plus 1, and since it's raised to the 1/2 power, I'm going to include the 1/2 power as part of what I'll call the u part of the integrand. Once you do that, the rest of the integrand, the x minus 3 in the numerator and the dx differential, will be part of the du. I'll call that the du part. I want the du part to be at the end, and the x minus 3 is part of the du part, so I'm going to physically shove the x minus 3 out of the numerator over to multiply the dx. Now it's perfectly okay to do that, because that's like x minus 3 over 1, so you haven't really moved it from the numerator in theory. It's just pushed with the dx. But you cannot leave a numerator without anything in it, so I have to insert a 1 there. And you can see that doesn't change anything, because where you put the x minus 3 back up there, x minus 3 times 1 is just x minus 3, and you're back where you started. So I've manipulated this around so that it looks like step 5 said it should look. The u part is first, followed by the du part on the end. That's what number 5 says we should do. You can see already that because u is equal to the quantity x squared minus 6x plus 1, that's going to be the u substitution that step 6 talks about. But what about du? I can't do du yet, because if you look back down at the lower left, du is supposed to be 2 times the quantity x minus 3 times dx. But in fact, if you look back at what I've labeled the du part, there is no 2 there. The x minus 3 quantity is there times dx, but we're not seeing a 2. So that's where the part of number 5 that says that we can compensate by a constant factor if need be comes in. We're missing a 2 that we need in the differential looking in the lower left. We can insert that 2 only if we multiply by the reciprocal on the outside. The reciprocal of 2 is 1/2. Now what has happened? We already saw that the x squared minus 6x plus 1 is going to come out as a u in step number 6, but now the entire right-hand part is all du. So it in fact can come out, and now we're ready to do number 6, which says to substitute the u's and the du's. In other words, get rid of every x and every dx in the original problem and change them to u's and du's. And you can see it's already practically done for us. I'll copy it back down, and don't forget the 1/2. If you get carried away with all the integration, don't forget that constant 1/2 has to stay in the problem. But back to the substitution on the integration. The x squared minus 6x plus 1 becomes the u, and it's raised to the 1/2 power, and it's 1 over u to the 1/2 power. But everything else following gets absorbed into the du. Look very closely at this, because if you don't understand how the substitution worked, anything you do after that is just wasted time, because you're not going to be able to reproduce that consistently if you don't understand what just happened. So the setup in number 5 that allows step 6 to successfully take place is a key step here, and you've got to think it through and make sure you've got it. Very important, getting from step 5 to step 6. Because once you do this, you're practically home free. The one thing I would warn you about is that the general power rule for integration tells you how to take the integral of u to a power, but this is 1 over u to a power, so we need to do something about that. But luckily, we know that 1 over something to a power is that thing to a negative power. So in other words, 1 over u to the 1/2 is simply u to the minus 1/2. Now it looks like something that the general power rule for integration can take care of. As you keep working, do not drop that 1/2. You're not doing anything with it, but you need to keep carrying it along. The general power rule for integration tells you how to integrate u to the minus 1/2. And as you see, what it basically says is if you start off with u to a power that you want to integrate, you end up with 1 higher power. So we're going to have to figure out what is 1 more than minus 1/2. Minus 1/2 plus 1 is going to be a half, because 1 is 2 halves, and minus 1/2 plus 2 halves is 1/2. So the power on u is going to be 1/2, but the formula also says that you have to multiply by 1 over that new power. So we have to multiply by 1 over 1/2. And that just means the reciprocal of 1/2. 1 over a fraction just flips it. So 1 over a half is 2. In other words, the reciprocal of 1/2 is 2. Don't forget that. And also don't forget, this is an indefinite integral, so you have to put plus c. Now it's a matter of just tidying up the arithmetic and getting rid of the u's. 1/2 times 2 is just 1, so we end up with u to the 1/2 plus c. And the u's were what we put in there. They weren't in the original problem, so we have to get rid of them. But we're also running out of room at the bottom, so I'm going to take that u to the 1/2 plus c and write it up top and continue from there. Step 8 says, the final step, substitute the x values back in. So u is the quantity x squared minus 6x plus 1, so we substitute it back in, and there you go. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integram that you started with. If you do, you know you got your integral right. In any case, there's your answer. Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of substitution by matching. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Now we want to start through the steps. The first step is to set u equal to the expression raised to the power. Now if you have any doubt about what u should be, I'll give you a little tip that's especially useful in the beginning here with these types of problems as you're learning. Later on I think it'll become second nature, but here's the tip. If you're ever in doubt about what u should be, choose u to be the expression with the highest power. So for this particular problem, you've got an expression that could be u, maybe the 2x cubed plus 4x. You've also got the expression 3x squared plus 2. But 3 is higher than 2, so I would suggest, according to that tip, to choose u to be the expression with the higher power. 3 is bigger than 2, so I'm going to let u be 2x cubed plus 4x. Later on, as you build intuition, you won't have to formally think about this so much, and as you get to more complicated problems, you'll be able to figure out a way to avoid having to even think about this tip. But right now, I think it's very useful. Then you go to step 2, which is to compute du dx. That's the derivative of u with respect to x. That's 6x squared plus 4. Of course, the goal is to solve for du, which is what step 3 says to do. So you want to multiply both sides of the equation by dx. The dx's on the left cancel out, and you're left with du equals the quantity 6x squared plus 4 multiplied by dx. Now, anytime you see a differential that has a common factor in it, it's probably a good idea to factor it out, and you'll see why in a minute. And if you don't need it factored out, you can always go back to the form of du which doesn't have it factored out. But as a matter of course, that's usually going to be what's required. So I noticed that both the 6 and the 4 have a 2 as a common factor, so I'm going to factor the 2 out of there, and that leaves me with 2 times the quantity 3x squared plus 2 all times dx. Now you can kind of see why that probably was a wise idea, because if you look back at the original integrand, you'll see a 3x squared plus 2 in it. And had you not factored the 2 out of the 6x squared plus 4, you might not have noticed that. You'll get better at this as you do more of these problems and practice more and more. Step 4 says if the integrand has a numeric, just a constant factor, in other words, a number, as a factor, move it outside the integral. There aren't any numeric factors in this one, so you don't have to worry about step 4. Step 5 is probably the step that you have to give the most work to get through it. But it says reconstruct the integrand so that the u part is followed by the du part, remembering that we can compensate by a constant factor if needed. Now all that really means is you're going to let your u part come right after the integral sign, and you want all of your du part to be at the end of the integral. And if you don't get an exact match with the differential you just calculated down here in the lower left corner, then you have to make that adjustment by a constant factor. And so let's look at that. The first part, the thing that you called u, that whole power, u to the power, that's what I'll call the u part, and it comes right after the integral sign. Everything else comes to the end and becomes part of the du. So the u part will also include the exponent. So u is the expression 2x cubed plus 4x, but when I say the u part, I'm also including the exponent. And like I said, the du part is everything else, and you want it to be at the end of the integral. Now we're set up perfectly to finish this problem off, but the key to knowing whether in this step 5 that you need to compensate by a constant factor is looking at this differential in the lower left corner and seeing if it's an exact match already. And what you'll notice is it's almost an exact match. There's a dx in both. There's a quantity 3x squared plus 2 in both, but the integrand does not have that 2 that we need. So you need to look at what's missing. There's a constant factor 2 that's missing, and you can put it in there. Now what I'll do here is I'll just space it out a little bit so I've actually got room to put the 2 in there. Once I make a little room, I'll just put the 2 in there. But you can't just put the 2 in. You have to compensate by multiplying by the reciprocal on the outside, and the reciprocal of 2 is 1/2. Don't forget that. That's important. So where do we stand? Look at what we've done. The u part is the part right after the integral sign. The rest of it is the du part. Now the question is everything completely matched? Well, let's see. Don't forget also that you have to keep copying that 1/2 down, even though you're not doing anything with it right now. You do have to copy it down. The u part is perfect. It's going to be the expression 2x cubed plus 4x is the u, so it's going to be u, and it's raised to the 3rd power. That's perfect. But look at the du part. Because I put that 2 in there, it's now an exact match. Looking in the lower left corner, it's an exact match for what we're calling du. And the goal is, the original problem is full of x's and a dx. When you finish your substitution, there should be no x's or dx's. There should only be u's and du's. And that's what we have here. So to continue, copying that 1/2 down, we are now ready to evaluate that integral, and we know how to integrate u to a power because we have the general power rule for integration. And it says you can integrate u to a power and you end up with 1 higher power. In this case, the 3 goes to a 4. But you also have to multiply by the reciprocal of that new power. The reciprocal of 4 is 1/4. Don't forget that. Also, don't forget that for an indefinite integral, any indefinite integral, you have to have a plus c. Now we can tidy things up a bit. A half times a fourth is an eighth. So you have an eighth times u to the fourth plus c. We're sort of running out of room, so let's move that expression up top so we can continue. And the only thing left to do is to get rid of the u. Remember, we put the u in there. There was no u in there in the beginning. So we go back and replace u with 2x cubed plus 4x. And there you have it. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer.